We've been talking about using scalar line integrals to find the total mass of a wire with variable density and maybe given by a parameterization. That's helping us understand why scalar line integrals are given by the formula that they're given by, and why ds is what it is. But it's not the only meaning and the only use for scalar line integrals, total mass. We do other things. For example, a wire runs along the curve x cubed equals y squared for 0 less or equal x less or equal 16. This example, this crazy curve again. Its density is 2 grams per centimeter. Okay. What is the location of the center of mass of this wire? We found the total mass. Where is the center of mass? And what did we find for that total mass? It was 129.898. Okay, well, the center of mass is located at the point x bar, y bar, where x bar is the average value of x along this wire. So 1 over the mass times the integral of x times the density times ds. And that comes out to be, or if we keep setting that up, 1 over the mass, the mass that we found earlier. This curve is parameterized from t equals 1 to 4. It's parameterized by x equals t squared. Our density in this question, the density is 2. And ds is something that we've worked out in the previous couple of videos for this curve. It was square root 4t squared plus 9t, 9t to the 4th dt. And remember, this was the magnitude of r prime of t dt, where r of t was t squared t cubed, and then you can take the derivative and find the magnitude of that derivative. It was this square root 4t squared plus 9t to the 4th. All right, that's x bar. You'd have this integral and then divide by 129.898. We can set up the integral for y similarly, or y bar rather. Y bar is the average value of y. It's 1 over the mass times the integral of y times the density. It's 1 over the mass times the integral for t from 1 to 4. Y is t cubed times 2 times square root 4t squared plus 9t to the 4th dt. Why do we integrate x times the density or y times the density? Well, if you imagine breaking each piece up into little segments, and you're trying to count the amount of x or the amount of y total. So each piece has a x location times its length to tell you how many x's are along there, times its density, because the heavier pieces count for more than the lighter ones. So hopefully that helps explain why we take x times rho times ds and y times rho times ds. I'll leave it as an exercise if you want to try to evaluate these. We use a similar trick to one of the previous videos. You can pull out a factor of t squared from this square root, or even a factor of 4t squared if you like, and then see how that goes. Good luck. I think I have one more example to set up and sketch through. So join me for one more example after this.